I've been requested to do a video on the cross product, and it's special circumstances because I was at the point on the physics playlist where I had to teach magnetism anyway, so this is as good a time as any to introduce the notion of the cross product. So what's the cross product? Well, we know about vector addition, vector subtraction, but what happens when you multiply vectors? And there's actually two ways to do it, with the dot product or the cross product. And just keep in mind, these are, well, really every operation we've learned is defined by human beings for some other purpose, and there's nothing different about the cross product. I take the time to say that here because the cross product, at least when I first learned it, seemed a little bit unnatural. Anyway, enough talk, let me show you what it is. So the cross product of two vectors, let's say I have vector A cross vector B, and the notation is literally like the times sign that you knew before you started taking algebra and using dots and parentheses. So it's literally just an X. So the cross product of vectors A and B, it's equal to, and this is going to seem very bizarre at first, but hopefully we can get a little bit of a visual feel of what this means. It equals the magnitude of vector A times the magnitude of vector B times the sine of the angle between them, the smallest angle between them. And now this is the kicker. And this quantity is not going to be just a scalar quantity. It's not just going to have magnitude. It actually has direction. And that direction we specify by the vector n, the unit vector n. We could put a little cap on it to show that it's a unit vector. And there are a couple of things that are special about this direction that's specified by n. One, n is perpendicular to both of these vectors. It is orthogonal to both of these vectors. So we'll think about in a second what that implies about it, just visually. And then the other thing is the direction of this vector is defined by the right-hand rule, and we'll see that in a second. What direction is this unit vector pointing in? So what I said earlier is it's perpendicular to both of these. So how can something be perpendicular to both of these? You know, it seems like I can't draw one. Well, that's because right here where I drew A and B, I'm operating in two dimensions. But if I have a third dimension, if I could go in or out of, you know, my writing pad, or from your point of view, your screen, then I have a vector that is perpendicular to both. So imagine a vector that's, I wish I could draw it, that, you know, is literally going straight in at this point or straight out at this point. I hope what you're saying. Let me show you the notation for that. So if I draw a vector like this, if I draw a circle with an X in it like that, that is a vector that's going into the page or into the screen. And if I draw this, that is a vector that's popping out of the screen. And where does that convention come from? It's from an arrowhead. Because what does an arrow look like? An arrow, which is our convention for drawing vectors, but an arrow looks something like this. The tip of an arrow, it's circular and it comes to a point. So that's the tip. If you look at it head on, if it was popping out of the video. And then what does the tail of an arrow look like? It has fins, right? There'd be one fin here, and then there'd be another fin right there. And so if you took this arrow and you were to if you were to go into the page and just see the back of the arrow or the behind of the arrow, it would look like that. So this is a vector that's going into the page, and this is a vector that's going out of the page. So we know that n is perpendicular to both A and B. And so the only way you can get a vector that's perpendicular to both of these is it essentially has to be perpendicular or normal or orthogonal to this plane, to the plane that's your computer screen. But how do we know if it's going into the screen, or how do we know if it's coming out of the screen, this vector n? And this is where the right-hand rule, I know this is a little bit overwhelming, we'll do a bunch of example problems. But the right-hand rule, what you do is you take your right hand, that's why it's called the right-hand rule, and you take your index finger and you point it in the direction of the first vector in your cross product. And order matters. So let's do that. So you have to take your finger and put it in the direction of the first arrow, which is A, and then you have to take your middle finger and point it in the direction of the second arrow, B. So in this case, your hand would look something like this. I'm going to try to draw it. Let's see, my hand. Let's see. So your This is going to be, so this is pushing the abilities of my art skills. So if that's my right hand, my thumb is going to be coming down. Right? That is my right hand that I drew. This is my index finger, and I'm pointing it in the direction of A. Maybe it goes a little bit more in this direction. Right? Then I put my middle finger, and I kind of make an L with it, or you could kind of say like it almost looks like you're shooting a gun. And I point that in the direction of B, and then whichever direction that your thumb faces in. So in this case, your thumb is going into the page, right? Your thumb would be going down if you took your right hand into this configuration. So that tells us that the vector n points into the page. So the vector n has magnitude 25, and it points into the page. So we could draw it like that with an x. If I were to attempt to draw it in 3 dimensions, it would look something like this. Vector A, let me see if I can give some perspective. So let me see if this was straight down. If that's vector n, then A could look something like that. Let me draw it in the same color as A. A could look something like that, and then B would look something like that. I'm trying to draw a 3-dimensional figure on 2 dimensions, so it might look a little different. But I think you get the point. Here I drew A and B on the plane. Here I have perspective where I was able to draw n going down. But this is how this is the definition of a cross product. Now, I'm going to leave it there just because for some reason YouTube hasn't been letting me go over the limit as much. And I will do another video where I do several problems, and actually in the process I'm going to explain a little bit about magnetism, and we'll take the cross product of several things. And hopefully you'll get a little bit better intuition. See you soon.